So welcome to video one of the main part of B08 on data visualization. This introductory video will look through basic plotting with R, which we covered a bit already, but it'll also think more broadly about what we're trying to visualize with the data. So if you see here, we've got the plots of names over time here. Time's on the x-axis and the frequency, the log scale frequency is on the y-axis. You can sort of see the labels there, and that's something that we'll try to make later in this course. Of course, you can see that there's things that could be added to this graph, such as lines and adjusting the text arrangement, and we'll get to that later in the course too. So with there's three basic options available. Firstly, base graphics, which are plots like this. So very simple, black and white, a few points present. There's a layered based ggplot graphics, which are more complex, and they give you nicer, cosmetically more appealing graphs like this. And give more complex representations in terms of minimize the number of different components for the user to take in at the same time, and thus communicate more complex information more effectively. There's other options as well, such as lattice for data visualization, which can work very well too, but we're not going to cover that, so we don't have enough time really. So base graphics is great for really editing. You can do very complex plots with it as well, but it's very good for quick and dirty plots. ggplot is better for polished figures. So if you want to make something look really nice, or indeed if you're dealing with a very complex data set, ggplot is very good, but it has a longer lead-in time to get something working. And then if you have other extensions, they'll be for very specific circumstances only. So why do we visualize data? Because when we visualize data, we see more things than might meet the eye. So all of three of these plots have correlation coefficients of 0. So you can appreciate that point there. There's three very different things going on. If you look at these graphs again, all these correlations are 0.7. There's a positive correlation here, but you can see here there's some sort of signal in this shape here in the first graph where there's something going on with the way the data has been transformed. In E, there's two different groups. In F, there's an outlier. G, you got kind of some sort of multi-level distortion going on. H, you got another outlier again. And I is the same, but it's a categorical group for the x-axis. So you can see why you need visualizing data effectively is important. An example of this was John Snow's map of cholera when there was a significant cholera outbreak where 500 people were killed in just as little as 10 days in 1854. And he used a visualization of the deaths around the area to work out the potential source of this cholera outbreak, to identify it so that action could be taken. But this was through visualizing it that he was able to deduce this. If we look as well at artistic images, we often see different things in different ones, and each has a different composition, has a different coloring scheme, has a different artistic effects that are very, very apparent and very, very obvious. But when we look across different images, we really see that they're very, very different, and yet they all can communicate something aesthetically pleasing, or maybe it's a very powerful message. There's different things, and we really have to think about what works for our particular data set. And there's no particular perfect option either way, whichever we're looking at. So you can think to yourself, what are your favorite figures? Why are they your favorite figures? What kind of visuals would you suggest for others to work with? If you're trying to give advice, that's often a good starting point for yourself. What do you think works well? A classic example of this is another map of cholera epidemic, 1885. It's a lithograph, an oil painting of the deaths and the weather at the time by Ferran et al. So you can see there that we have the temperature, the pressure, and the mortality frequency there. If you zoom in, we can see more patterns across the different days, where you have the temperature changes, the highs and lows through the day, and then the pressure as well. And you can see the mortality rates and other data embedded inside this graph. So it's really a scientific graph, but it's visualized in a manner that is with which many people can engage easily. Another example of this is looking at the extent to which newborns are prone to measles infection, pre-vaccination, and that's very, very common before. Initially, in this area of London, measles rates were talked about using deaths rather than cases. Thankfully, we're now looking at cases, but you see here the square trend for cases. You can see that there's episodic outbreaks of the deaths. You see then when vaccinations were introduced in 1868, that the number of cases then declined dramatically. So you can see there that the square root of C is the is shown there in our background. And you can see the episodic nature where you've it's endemic and epidemic at the same time. You can see the general decline. So you see how this graph embeds two different colors to kind of identify clear shifts, three shifts through the phases. And we can also see that they use the same single y-axis scale by taking the square root of the cases, which is a decent proxy for what's going on. We have other options, things like bar graphs, which are not effective for visualizing different things. It doesn't capture what's going on. This could be a table much more easily. There's other options, many options. We'll talk about them further. Cumulative curve is an increasing frequency as we progress through a distribution. We have box plots as well, and we'll visualize them with Basor. We have distributions like this. We're looking at histogram of the different options, and we just need to consider how to what extent we bin them together in different groups. We have comparisons between different groups as well. You see that these are two histograms put against each other to show a sex and age distribution for a population, and that can quickly communicate changes in the frequency for different categories and also between two different groups. We also have similar ones in violin plots as well, which are essentially box plots. So there's many different types of plots. You'll be most familiar with things like scatter plots, but there's variations you can do in ggplot like bubble plots. You might be familiar with bar charts, which can be effective, but have a very specific use. And there's variations on that, like line charts and column charts as well, histograms, line histograms. And then if you look further down, we've got things like stacked charts. We avoid bar charts because they're not effective. These are just examples of what we're looking at. So you can also think about when we look at what's effective for representing a ratio of two different values, like 1 and 7 here. There's work on showing that the lowest precision way of doing this is to use a ratio for the two different colors, like 1 and 7 here in light and dark. An angle is better, but not effective. An area is medium precision. A length is more effective because people understand that difference between the 1 and 7 value more quickly. And then we have a position. Position on an axis is the most effective way of distinguishing these two features. If we think about illusions that may distort data as well, we can think about not scaling the y-axis with 0 is a common issue. We also have the stacked bars, where the baselines are very, very difficult to start with for the gray and light gray here. If we have different colors for different nodes, then it may be difficult to scale the area properly, as you can see represented by these circles here. And then we have intensity values, that the backgrounds that are used for these intensity values can also have big effects. We can go further about looking at global stats. So dot plots can be effective for showing a numeric summary of data. We've got stack bars as well, bubble maps, slopes of graphs, and then heat maps that we'll talk about as well. We also have challenges in visualizing communicating certain data sets, which may not work. So we're talking about subtle differences, such as maybe the pairs here, A, B, C, D, E, F. It can be hard to represent them visually. So it's maybe easier to highlight certain things. I will look at GG highlight how we can do that to identify ones where maybe there's a change that's biologically interesting. So we also have to think about what's the message we're trying to communicate. So if you look here at the change in temperature in Fahrenheit over time, on the one hand, we may want to represent that with 0 intersecting the y-axis with the x-axis. However, the meaningful difference might be to represent the more recent change that we've identified. We also have to consider that units of Fahrenheit also can affect that. So what's our starting point and what's informative in the context is very, very important for determining what figure to use. We look here as well, this graph is somewhat deceiving. That look the difference between the start here at value 3, x equals 3, the difference is 1,000, because this is a function y is equal to x cubed plus 1,000. When we go up here for x is 19, the difference is still 1,000, but it looks like it's less. So these look like they're converging, but they're not. It's just an artifact of the graph. So we also have to consider that as well. Another aspect of plotting is that if we use the normal color palette with red and green, like red and dark green and dark red, like here, for colorblind friendly plots, and might have to use other colors. That may not work effectively if we're using something close to green and purple. So what we might do instead, and the first option is to use change the point type. So we've got diamonds and circles here on each plot to make them more easy to distinguish. And we'd also use a safer color palette that's more friendly for colorblind people. So when they look at this graph, instead of seeing the one here where it's very difficult to differentiate, they'll see this one here where there's 2 different colors. So orange and blue is more effective there. We also think about point types. So unfortunately, the standard ones in Excel are not very effective. However, there are ones that are known to be effective based on humans' perception and testing to show that they work more effectively for visual light features for people. We also have to think about how we can better distinguish 2 different data sets. Those ones that are less powerful. So the shape helps, but it's only a small effect. The color helps. Having separating A and B are 2 different data sets positionally is more effective. And the best one, which you probably tend to do, is to connect the lines. And that might be something you do intuitively, but it's important to make it clear to the viewer what the 2 different data sets are. Another example here is we've got different metrics here, social security, earnings, and so on. And we have them from 1962 and 2007. And here they're blocked by year. But if our comparison here is the difference between social security for 1962 to 2007, we might want to group them together more easily. And we want to differentiate the different groups here, but plotting them in different colors. So you can see that each is different because they're in different colors, and they're grouped together to make it more easily to identify that there's groups, the differences between them. We can also think about humans, our ability to interpret graphs. So in which process is easy to identify these groups? So you can see here that the direct labeling is the easiest and simplest. ABCD is obvious because it's marked on the lines. We don't need colors or anything else. Whereas if you go color legend, we'd look at red and then go down across the groups and search for B, and then go back to red and then do the same for blue. And your eyes are moving around a lot, so it's not as easy to do. And it's the same here. We've got symbols, but it's the same. Same pattern. We have to look across the legend to see what's happening. Another feature is that there's been work on our collective poor ability to distinguish between linear graphs, which we do effectively, compared to log ones. So what's shown here is you've got population size versus distance from the edge for a black graph and a dashed graph. When we log scale these, you can see the coordinates are transformed here on both axes. And here, they seem to be parallel effects. So you might interpret that as having the same magnitude of the effect for the distance from the edge on the population size. However, because these are logs transformed, let's It's not actually the same at all. So another thing that you see very commonly is these kind of bar plots where it's really not an effective visualization, and we have to think of alternatives. So these are bad ways of representing data. They're really, it's diabolical because you're taking the underlying values that you could plot very easily, and you're just summarizing them and not showing the original data, because the heterogeneity of each group is crucial for what we're representing. So these are not effective visualizations, and they should be avoided at all costs. So we're looking at your binning continuous variables as well. So we've got people from 18 to 55, 56 to 69, and then 70. So age is a continuous variable, but it's binned. That's a bad choice. And this was published in the Lancet as well, which is one of these big multi-author papers. So they did think about the visuals very well. The model isn't mentioned. They have p-values here, but the model, what's the model talking about? The test performed, statistical tests not mentioned. They just have small p-values dangling over their graphs. The standard error is shown, but not the standard deviation. Number of samples that are not mentioned. The y-axis is scaled and cut, as you can see, and the sampling group is could be well be imbalanced if we consider the 18 to 55 group together. So, our summary is that we have bad ways of doing things like our plots up here, and then we've also good ways of doing things which are much more effective and much more informative for viewers. So when we do this in R, you'll try to set your working directory, and what you'll do is import our group of Irish boys' names into R. We might manipulate it just to remove an extra row there. But when you do that and do that for the girls' names as well, and you'll be able to count, look at the structure of the data, and we'll be able to do some basic plotting with R. So if we do that this is for the girls' names from 1964, we can plot them with a simple plot. We can add a grid, and we can also do a density plot. And you see that there for our first basic plot, we do the unsorted data. We can look at the frequency of the different girls' names in 1964, and the surprise if you can guess what this very common name is. If we then sort them, we get a more clear distribution. So most names are very rare, and there's a few that are more common. And the density plot shows the same thing. So we can see as well that when we do basic plotting with R, we have many different line types that we can use. So we change them from solid to dashed, dotted, and so on. We can also change the point type from round or square. We can also change the colors to a very diverse range of colors. Just bear in mind color blindness as well. There's also different graphical types we can use. So if you're using Windows, raster graphics can be more effective, like PNG, TIFF. If you're using a Mac, vector graphics, PDF, are typically more effective at maintaining high image quality on your computer. And then if working between the two, then you may have to think carefully, and it might depend on the destination source, if it's a journal or if it's a PowerPoint slide or whatever you want to show at the end. So that kind of covers this video. We looked at generating data, we looked at different plot types and what to do, what's effective for that. And we looked briefly at how, in the demonstration video, we look at how to write out a plot. So that's the end of this video. See you in the next one for more on how to learn about ggplot.